I want to talk a little bit about regression, and I have some data here. We see we have a table on retail sales, and um, I have one sample here of uh, 8 different stores: Walmart, Kroger, Home Depot, and so on. So we have 8 different stores. So we have a sample. Um, uh, a sample of 8 different companies here. But what I want to do is collect 2 pieces of information from each of those companies. I'm collecting total sales in billions of dollars and then profits in billions of dollars. So Walmart had total sales of that's $315.6 billion, right? And Walmart also, out of that sales, they had profits of 11.2 billion. So each one of the stores has that listed. So we want to compare these 2 variables, these 2 quantitative variables, total sales and profits, and we're going to plug this stuff into the calculator. So first, we're going to look at the TI-84, and uh, when I hit stat, it starts here in edit, and we're going to go over to tests. And then I'm going to go down almost the whole ways to the bottom under tests. Linear regression t-test. So we're going to do a regression, right? And it says t-test. So that's familiar, right? We ran t-tests before, and there's our own regression test for R. Remember, R is that value is correlation, and then we're going to use the idea of correlation to help us run this regression test. And again, it's linear, so we're trying to see when we plot these ordered pairs how well they're going to line up in a straight line fashion. Okay, so let's go ahead and let's go back to stat and edit here first. So enter. I need to enter the data, and I'm going to clear, enter. I highlighted L2 and I hit clear and enter. I want to clean out these data columns. Go up to L1 and hit clear, enter. And then I need to put in these values. So for the total sales in billions, I'm going to put this in 315.6, 60.6, and so on. So we're going to put these all in so you can see how these are supposed to go in. 81.5, 60.1. So I'm putting all the total sales in that column first. And $7.8, 16, and 30.8. Okay. And again, these are this first column right here, go in this first column here. So we have a set of data values here. So here's like one sample, right? We're going to comparing that to another sample from those same 8. So when we have, it's kind of like a dependent t-test in a way, right? When we did dependent t's, we said, well, it was dependent if we had one sample tested twice. The only difference here is that when we did one sample tested twice with the dependent means t-test, it was the same variable on both tests. We tested like VOCs before plants and VOCs after plants were put in. And here, again, these are not the same two variables that we're testing. It's not a pre-test, post-test design. All right, so 11.2, 0.98 in billions again, and 5.8, 1.1, 2.4, 0.6, 1.1, and 1.1. Enter. All right, so again, hopefully we got these in correctly. And it looks good. So now we can go again. Now we got the data in. We got two different variables here, two different sets of data, right, from those same 8 companies. And so I can run a regression then. And, you know, this is a bunch of points. Let's go back here and look at it. And I put these in a program called Desmos. And you can, if you don't have the And if you don't have the graphing calculator, you can use Desmos if you don't, and to work these problems. So basically, again, you type in desmos.com, and you'll see here you go in, and on the left, click on the plus, and it'll say table. So that's how I got the table to show up in here. Okay, and then the graph, this thing, I need to change my Y values because they're so much bigger. These are smaller than my X values. These go from 0 out to like 315. So I can go over to here in settings, and my Y axis, it's too big. I want to go from, actually, this is going to go from, let's make it -10 up to, and my values only go up to 11. So from here, I'm going to go up to like 15. Right. So that looks a lot better. We could even bring it down a little bit more, and let's backspace that to 13 or even 12. Okay, so here's my first quadrant, and here's my graphs, right? Or my points. So I get to see kind of what that looks like. And you can see it does kind of have, this is like we would consider an outlier. And that was here, that's Walmart value. And then it looks like it's linear. Again, you know, if I ignore this for a minute, they are kind of going up this way, right? So we looks like a positive correlation. So our line, what we want to do here is see how well do these things fit a straight line. And I could get a line by picking 2 points. So in algebra, we would say, okay, I could pick this point, and I could pick this point, and I could draw a line between those two, and that'd be kind of a line through these. And then you say, well, maybe, what if I picked this point here and this point, and I drew a line through those? And it would fit those probably better. Well, we're kind of guessing that way. You know, there's got to be some mathematical way that puts the line right through the middle of kind of the average line that goes right through all of those points, right? And there isn't. the one in this course we call least squares regression model. And what we do is we really kind of take and look at all the points on the lines and see how far they are away from a particular line, and then sum them up and look at where the sum of the squared deviations from the point to the line are at a minimum. And that's called the best fit line. So we're trying to find, so regression really is just trying to find which straight line for which linear function, right, that y equal mx plus b, will go through those the best. All right, so how do we get that? Well, we're going to use calculator to do that. And that's why we put the data in here. We just go to stat and tests, and we're going to go way down there again to the linear regression t-test, right? Linear regression t-test, hit enter. And the x values are our independent variables here. These first ones here are in L1, okay? The dependent variables, these are in L2, right? There, that's our profits. And these are our parameters, our beta, our rho. So these are the slope and intercept parameters. And we don't have any equation listed there. We don't have it yet. Now, we can leave this at not equal to 0. The hypothesis, or we start out by saying that, there's no linear correlation here. There's 0 linear correlation. So that's what these zeros are representing. And then when we run a hypothesis test, we see if that's could be different from 0. So right now we start off by saying that it's regression or correlations equal to 0. These parameters are equal to 0. So let's hit calculate. Enter. And then we have some values. All right, so we got this data. I'm going to take this out of here. And we're going to look at this stuff over here. So this y equal a plus bx, all right? Now, in algebra, we were talking about how in algebra, typically, we write this as y equal to mx plus b, okay? And that's the same thing, except they just like flip these around and a and b or whatever. So this, again, was the slope-intercept form for the equation of a line. This was the slope, the m, and the b was the y-intercept. All right. So over here, right, this again, this was the way we wrote it in algebra. Now, in this calculator, I'm going to write it as y equal to bx plus a. Okay. So again, we're going to just remember that this is what we are really doing here, but we're not using our same lettering. So here it is. This is the slope and y-intercept. So y equal to, well, we need the b, and right there's the b, 0.035 x, okay, plus, I need the a, 0.286. All right, so here's our slope-intercept form of the equation of a line, and we talked about that a little bit when we were solving equations. And now, again, so regression, typically, the biggest thing people use regression for is prediction. So you can use it to test theories and so on, try to maybe understand cause-effect a little bit better. But initially, we're just going to talk about prediction, right? So this is a prediction equation. And what's the prediction equation for? Well, our data was about sales and profit. So we could put in here sales and then calculate what the profit would be. So let's say that we have X our sales X, right, let's say is 1,000. 1,000. Okay. So I have Y equal to 0.035 times, and I put an X, 1,000 plus 0.286. All right, so let's see what we get. Y equal to, so 1,000 times this, it's 10, 100,000. So I tried to make it easy. So this is going to be 35. This is 35 plus 0.286. Okay. So Y equal to 35.286. And that's pretty much it then. What that means is if we sell 1,000, that's in billions, right? So that's a lot. And we should come up with a value around 35, or that's our profit, right? So this is our sales, our input, our profit, right, is our output. Okay. Let's clear this out. Clear canvas. And let's look at some other values out here. This T. So the T is the test statistic, 6.8. All right. Is that a big value? Well, yeah. Plus or minus 2. We're talking about the T distribution. 6.8 is a pretty big number, right? So if we look at the p-value here, and again, I'm just talking about these numbers. They may or may not be, of interest to you, but I'm going to put these up here for now. And so, but in the 2023, the elementary stats, we've already talked about these things before. So this says 4.9 E -4. So e to the -4 means, right, this P is equal to 0.00049. So you move this over 4 places to the left. So it's here, 1, 2, 3, 4. So that's a very small number, right? That would definitely be reject that original hypothesis of 0. Now this S, so everybody should know what that is. S is standard deviation. That's the variability of that scatter of points about the regression line. And looks like we can go down some more. And we got a couple more values that we can go down, right? I'm going to put R next. R equal to 0.94. Okay, so again, I got this right here. So there's our correlation coefficient. Remember, correlations, we talk about either positive or negative. So this is positive. So the line should be going up. And then the value is close to 1. So it's a very strong positive correlation. So this is pretty good, right? This is a good predictor because this is very strong positive correlation, right? The highest you could get is 1. Remember that R value goes between 1 and -1. Anything around 0 is considered weak. Anything out in either direction. So this would be strong positive, strong negative down here, moderate negative in the middle, not moderate positive in here. and then right around in the 0 week. Okay, so regression gives us some things we've talked about already. It's the R value we've talked about, correlation. But it also gives us one other thing here we want to talk about, this R squared. Okay, so R squared is equal to 0.885. All right, so pretty close. Now, does that mean if you take R, this number here, and you square it, and you get that value? And yes, that is true. It works out very nice like that. And I'm going to just take my calculator, and you could do it on the screen, but I'm going to just verify that 0.94 squared is equal to 0.88 something something 54 and so on and so on. So we rounded that a little bit, but so it'll remember we have a little bit of rounding going on. So it doesn't come out perfectly, but it's pretty darn close. So this is a very important regression number. It's called the coefficient of determination, and this has to deal with what we refer to as the explained variation. Okay. Because if we're going to use this thing for prediction, well, we know statistics, there's always error involved. So if we have that predictor equation that we were going to use, well, how good is it? All right, that's what we would like to know, is how good is that thing? And probably the best way really statistically to tell, again, is this R squared value. So I'm going to take this off here. Oh, there we go. And leave this up. So the plot, let me just bring this back over here so we can look at it. There we go. So here's our again table, and there's our points, right? So it's actually pretty linear according to this, and when it goes through these points are all very, very close to the line. And that's a good thing. Okay, that's a good thing. And let me just move this over here for a minute. Now what I want to do is put that line in there. It'll actually I'm going to click right down here. I'm going to put in Y, and I'm trying to find the symbol. There we go. That tilde kind of symbol thing is, or let me just back that up. Y sub 1, and that tilde is kind of like, for now, the equal to, and then M, and then times M sub 1, M X sub 1. There we go. And that is going to be plus B. So again, Desmos is using that y equal mx plus b, the algebra form. But you'll notice here, our R value was 0.94 something something, and you'll see that they've got, 0.941. They rounded it also. Here's our R value. And R squared 0.885, they got 0.8855, and again, we kind of rounded in there, so they rounded up. But this is kind of nice. We get to see the line and how close the points are right, to that line. Again, this is called the least or line of best fit, least squares regression model. And uh, we have the explain variation. So we want to know is how good of a predictor, again, is this going to be? Well, we can look at this R squared value, and it's saying that it's about 88.5% efficient, meaning that you have really one other option. If you wanted to kind of guess at what the profit was going to be, you could look at the average profit for a lot of companies and say, okay, well, on average, this is what the company makes. And so we've talked about averages, and they're very important in statistics, but they have limited value. And when we're trying to predict something, the average is really not a great predictor. So when you do regression, it's better. Okay, how much better? Well, in this case, 88.5% more efficient. We've got a lot of the variation that we would normally see around the mean explained by this line. If we put in the mean, it would just be a line going out this way. And these points, they're not that close. This one would be way off. This one, these, not very close. And this line, right, the closer it is to the points, the better prediction. This is our prediction line. Now, the distance from the point to the line, obviously there's some error, and the error relates to how far the points are away from the line. So each point has a residual, what we call residual, or distance that it is a perpendicular distance that is away from the, not perpendicular, but this perpendicular to the x-axis. So this distance from here to here, or the difference in the y value of the actual point placement and its predicted value on the line. If the point was on the line, we'd measure these differences in the y values and say that's our residual. So each point has a residual associated with it. Some are very tiny residual. This one, these are tiny. This one's a little bit bigger residual. This one has the biggest residual or distance away from the line, or vertical distance. And so that's pretty much regression. Now, again, this is linear regression, and there's lots and lots of other types of regression, and there's lots of things that you can, do with regression, and why you might want to use it, and so on. But for our purposes, just talking about prediction and these values, and again, in this case, we are well below 1% on our p-value. We would reject. Our significance level, we could have set at 5%. We have a large t-value, right? Our p-value is very small. The 1.35, again, has to deal with how much overall these points are scattered about the line. So see, this number is pretty small. And we pretty much covered all of those values. You'll see the error plot. So we get to see, right, those values of the errors or the residuals. See the residuals here, E sub 1, right? These all go with these points. This one goes, right? And so on. So, okay, we're gonna stop there and head to chi-square next.